Hello and good evening, everyone. Thanks for hanging around. So I was just reading. So I'll just share my screen and we can start in a minute or two. So good evening, everyone, and welcome to the last session. That is week on, and so yeah, this would be the concluding session. And as you might have gone through the lectures, you would have learned about closed loop control, right? That is how to model the system in as using state equations. That is using the if you have L and C in a circuit, then you obviously know that you have the relations of V is equal to LdI by dt and I is equal to C dV by dt, and those are kind of the fundamental equations, right? And with that, you kind of try to model the converter in frequency plane, right? So once you have the planned transfer function, you kind of design the um, controllers for uh, regulating your output voltage, correct? So typically you would have learned about the conventional, I think my camera is not on. Yeah, so typically you would have learned about the PI controllers, correct, and how you design them, right? That is how you place the values of PI so that you are able to get zero steady state error, right? And of course you want to have some bandwidth. So based on the PI. So based on that, we will try to solve some problems today, and at the end you can ask for any doubts, okay? Okay, so the problem number one goes as follows. That is, a boost converter is controlled at an output voltage of 25 volts. Correct. The input um, has a 20% tolerance around the nominal value of 15 volt. So what is the percentage swing in duty ratio? Right. So I think this is a pretty simple question. Okay. So your V naught is 25 and V in is given as 15 volt plus or minus. Okay. So V in is given as 15 volt plus or minus 20%, right? And so what is the percentage swing in duty ratio? They are telling that percentage swing in D is equal to what? d max minus d min divided by d nominal into 100. Okay, so I think this is very simple, right? So this is a boost converter. So you know the relation is V naught by Vn is equal to 1 by 1 minus d, correct? So you know the variation
Excuse
of
me,
V.
sir. Your
Sorry,
voice is, your screen is not visible.
my screen is not visible.
Yes, sir. Not visible.
Just a second then. For my face. Okay, I will reshare once again. Now can you please tell?
Not
Is
yet,
it
sir.
visible now?
No, sir.
Okay. In mine it says the screen is visible. Just a second, I will stop and
See,
stop.
it's visible.
Sorry,
It's visible screen.
it is visible. Are you able to see my slide and all?
Yes.
Okay, so Akshit, like, can you log out once and then log in once again? Yeah, thanks. Is it now visible, Akshit?
Yes, ma'am. Yes, sir.
Okay, fine. Thanks. I'll just continue from here. I hope my slide is visible. So the first question was, a boost converter is controlled at an output voltage of 25 volts. The input has a 20% tolerance around the nominal value of 15 volts. So what is the percentage swing in duty ratio, right? And they have given that the percentage swing is D max minus D min divided by D nominal into 100. So I think this is a simple problem, correct? Because your V naught is given and V in is given as 15 plus or minus 20%. So you just know that for a boost converter, the input output relation is something given by 1 by 1 minus D, correct? So from this, you can calculate what is the value of D, correct? So you can just substitute for the extreme cases of V naught, extreme cases of V in, correct? And as also for the nominal case, so you will get what is D max, you will get what is D min, and you will get what is D nominal. Okay, so once you know this, then the percentage swing can be determined from this formula. Is it fine, this question? I'm not doing it because it is very simple. Okay, so for example, D nominal, you know, it is going to be 15 divided by 25, correct? 1 minus 15 divided by 25, right? This will be your D nominal. So similarly, you can find out what is a D max and D min. Okay, that is 1 minus D max will be 15 plus 20%. 15, sorry, 15 minus 20% of 15.2 into 15 divided by 25. Okay. So I think this is simple, right? V naught by V in is 1 by 1 minus D. So from that, if you calculate, it turns out that your D nominal will be 0.4, D minimal is 0.28, and D maximum is 0.52. So this is your swing. Okay, so 0.28 less than or equal to D less than or equal to 0.52. This is your swing in D for the given swing in V in. Okay, so with this you can find out what is the percentage swing. So percentage swing was how much? Percentage swing is given in the problem. Okay, that is, you see over here the percentage swing is D max minus D min divided by D nominal. You calculate what is D max, D min and D nominal. So percentage swing will be what? So it will be simply D max
Sir,
minus
we are
D.
unable to see the screens again.
Oh, Now I guess it's visible, right?
Yes.
So I was telling about this problem that your percentage swing is going to be d max minus d min by d nominal. Okay, just calculate what is d for all three cases and just substitute over here, right? So this is a pretty simple problem. So the answer turns out to be around 60%. You can check later, right? So let's move on to the next one. A buck converter is controlled by current mode control and charging a battery. So the battery voltage is fixed at 12 volt. The slope of the slope compensation is chosen to be half of the inductor current slope during turn off. So the average inductor current is 5 ampere while the input is 20 volt. Now the input changes to 24 volt. What will be the average inductor current now? Okay, so try to understand this problem. See, buck converter operating in current mode control. So what is current mode control? Anyone? What is current mode control? Okay, so current mode control or constant current control, or some people also call it peak current mode control, is a way wherein you control the peak current through your device. Okay, that is, you keep the peak current through the device fixed to a particular value. So you will have a comparator, you will sense the device current. So once you see that the device current has hit a peak limit, you will turn off the device. Okay, so that defines the duty. So what they are telling us, the battery voltage is fixed at 12 volt, right? That is your V naught for the buck converter is fixed at 12 volt, right? Buck converter is charging the battery. The slope of the slope compensation is chosen to be half of the inductor current slope during turn off. So try to imagine what is the buck converter. So the buck converter is something like this. So you will be having a switch over here, and then you will be having the diode, and you have the V naught. So this is your buck converter, and you know that this is going to be V in, this is going to be V out. Correct. So if you assume this is the polarity, my VL is going to be V in minus V naught during the DTS period and minus V naught during the 1 minus DTS period. Okay. So this is your VL, right? So you know that the voltage across the inductor VL is going to be minus V naught during turn off. So during off scenario, the VL is going to be minus V naught. So what they are telling us, the slope of the slope compensation is chosen to be half of the inductor current, right? So if VL is minus V naught, you know minus V naught will be equal to what? L into delta I by DTS, right? And DT will be what? 1 minus DTS, because this is your turn off period, correct? So what is your slope from here? So slope or di by dt is going to be given by what? Slope is equal to what? Minus V naught by L, right? So given that your V naught is 20 volt, so what is happening? Slope is going to be how much? Slope is equal to, let's say M is M1. Okay, slope of the slope compensation is chosen to be half. So if your, let's say the slope is going to be M, this is your slope M, then the slope compensation slope, let me call it MA, will be what? MA will be M by 2, correct? Because they have told the slope of the slope compensation is chosen to be half of the inductor current slope. So inductor current slope is M, therefore half of that is going to be M by 2. And the average inductor current is 5 ampere. Okay. So the average inductor current is 5 ampere or I naught, correct? I naught is going to be 5 amperes, correct? So while the input is 20 volt, so Vin is going to be 20 volt. Now the input changes from 20 volt to 24 volt. That is what is given. What will be the average inductor current now? Okay, so the input has changed, and what will be the average inductor current now? That is the question. So, right. So the answer is pretty simple for this. You need not calculate too much. So point is, you see over here, we are doing slope compensation. Okay. And they have told that the slope of the slope compensation is chosen to be half of the inductor current slope during turn off. So the slope of inductor current during turn off is simply what? Simply V naught by L, right? That is minus V naught by L. So this is your slope. The slope is independent of your Vn. So since this is only V naught by L, this is only dependent on V naught. Okay. Input is changing to 24 volt. Only the input has changed. Output is still same, right? Because it is charging a battery, the output is still same. So your V naught has not changed. Okay. So V naught has not changed. Therefore, there is no effect, right? Even if your input changes to 24 volt, my inductor current is going to remain constant. Okay. The inductor current is going to remain constant because your slope is actually constant. Correct? Yeah, thanks for hanging around. I got logged out. I don't know why. Yeah, so as I was telling, the slope during the turn off is independent of your input voltage. So even if your input voltage changes, nothing is going to change with respect to the slope of the slope compensation, right? So average inductor current is going to remain same in both cases. Okay, so we'll go on to the next question. That is, in a closed loop system, the high gain of the proportional controller can cause dash. So, if, so what do we call as a proportional controller? That is, let's say we call it KP. Okay, so this is just a gain. You multiply your whatever is your plant transfer function. If let's say the plant transfer function is something like this, right? So I'm multiplying this with KP. So my equivalent plant transfer function may become something like what? It will just get shifted up, correct? That is, you're giving a gain to everything. So this will become this, correct? So everything will be shifted up, something like this. So your equivalent transfer function or equivalent gain will be something like this. Okay. So this is after multiplying with KP. Okay. So this is Kp into plant transfer function. Let me call it Gp. This is just Gp. Okay. So what has happened with this? So if you do this, you will obviously see that at DC, right? So if I mark it, this is your gain, correct? And this is your log omega. So this is your frequency spectrum, correct? In log omega domain. Okay, and this is in dBs, let's say. So what has happened is you are basically shifting your entire curve up, correct? So let's say this is 10 hertz, correct? This is 100 hertz, 1 kilohertz, and let's say 10K, 100K, and so on. Okay, so as you go lower and lower, obviously you don't have a DC with log scale because you cannot have a frequency that is 0 or DC. But point is, you can take very low values of your frequency as almost equal to DC, right? So let's say your switching frequency is 100 kilohertz. So if you consider 100 kilohertz, frequency of let's say 10 hertz can be considered as DC. Okay. Okay. So I was mentioning that if you consider, let's say, a frequency, switching frequency of 100 kilohertz, so compared to 100 kilohertz, the frequency of, let's say, 0.1 hertz or 1 hertz or 10 hertz, something like that can be considered as DC. So you will see that at very low frequencies also you are getting a very high gain. Okay. So let's say the gain over here was something like, let's say the gain was something like 40 dBs. Okay, originally to the plant.
Excuse me, sir.
Happen is if you multiply with a particular value of
Sir, screen
Kp,
is not visible.
screen is not visible. In mine it says screen is
It's visible, sir.
visible, right?
Yes, sir, it's visible.
Okay, I think there's some problem. Probably you should not go to full screen then. Then it might help probably. Okay, so as I was mentioning, initially let's say it was 40 dBs, and now you multiply with particular gain Kp, and let's say now it goes from 40 dBs to 70 dBs. Okay, so there is a shift over here, correct? Some from 40 to 70 dB. Now, if you go to the, let me take a new slide. So now let's say your steady state error, correct? So your steady state error can be written as something like 1 by 1 plus t, where t is equal to gh, correct? That is, t is your open loop gain, correct? So let me write t is your open loop gain. Okay, so this is your steady state error. If your t is very high, if t is very high, correct, then what would happen to ESS? ESS will be very low, correct? Very low. Okay, so that is the idea. If you have a very high loop gain, then your ESS will be low. Now you can tell, let's say you have two cases, right? In one case, T is equal to 40 dB, and in the other case, T equal to 70 dB. So in which case the steady state error will be lesser?
Sir, in
Can
70
someone
dB.
tell? Sorry?
70
70
dB.
dB.
Correct. So at high values of T, you will get low steady state error. Correct. And how did we get the 70 dB? By multiplying with the gain. By proportional gain, we multiplied it. So we shifted this entire plant transfer function from this to this. Okay. So that is why you will see that the steady state error is going to be lesser. So the point is, let's say the reference voltage is something like 40 volt. You might see that with 40 dB, Okay, so let's say instead of 40 for confusion, let's say it is 100 volt. Okay, so the reference voltage is 100 volt. With a system of T equal to 40 dB, you will see the output will be somewhere around, let's say, 97 volt. With 70 dB, you might see somewhere around 99 volt. Okay, there is a difference, right? So there is a better tracking with 70 dB. So higher your loop gain, the lesser will be the steady state error. So you can achieve better tracking. Correct. So that is the advantage with proportional controller. Okay. So definitely you know that it will not cause increased error. In fact, the high gain of the proportional controller will cause decreased error at the output. Agreed, right? Okay. So now we will move on to the next one. So you tell me, let's say you obviously see that with 40 dB, it will cross over faster, correct? So this is your 0 dB point. So let's say this is omega 1 and let's say this is omega 2. So what is this frequency called? Omega 1 and omega 2. What is this frequency called?
Angular frequency.
Sorry?
Sir, angular frequency.
Okay, omega is angular frequency, fine, but the frequency at which you are crossing over the
Gain
0 dB
crossover
point.
frequency.
Correct. So the frequency at which you cross over the 0 dB point, or when your gain of the system becomes 1, correct? That is in absolute value. That is called omega GCF, or that is what is called as your gain crossover frequency. Okay. And it turns out that higher your gain crossover frequency, or we call this as the bandwidth of your system. Okay, this omega GCF is known as bandwidth of the system. It turns out that higher your bandwidth of your system, the faster will be your response, right? If you have a high frequency system, then the bandwidth will be much faster, correct? So let's say you have a crossover at 10 kilohertz and a crossover at 100 kilohertz. So okay. So your response time will be what? It will be 1 by omega GCF. Okay. So let's say in one case you have 10 kilohertz as omega GCF, and in one case you have 100 kilohertz. Okay. So in which case the transient response will be faster?
100 kilohertz.
Sorry?
In case of 100 kilohertz, the transient
Correct.
response will be faster.
Correct. So at with 100 kilohertz, the transient response will be faster. So you see that you only multiply with a gain Kp, correct? You multiply with a gain Kp, then what happened? The entire curve, that was something like this, now has become something like this. Correct? Now it has become something like this. Correct? So your crossover frequency is now increased. So this was omega 1. Let's say this is 10 kilohertz and this was omega 2. This is 100 kilohertz. So now what did we see? Your steady state error has decreased because you have huge gain now. That gain has increased. The effective T has increased, and you also see that the crossover frequency has increased. So the response time will be faster. Correct? So response time will be faster. So there will obviously be improvement in the transient response of the system. Correct? Improvement in the transient response of the system, not steady state response, improvement in the transient response of the system. Okay. So let's say there is a step change in your reference, right? So if there is a, so what does this signify? So if let's say there's a step change in reference, so this is your Vref. You went from Vref 1 to Vref 2. There's a step change over here. Okay. Now, how does your system react, right? So in one case, it will turn out that, let's say if your system is 10 kilohertz, omega 1 is 10 kilohertz, then your system will respond something like this probably. Okay. That is, it will be kind of like an overdamped system. And now if you make it 100 kilohertz, then the response is going to become 10 times faster, correct? It will be 10 times faster. And you might see something like this, okay? Or if you even make it faster, you will see something like this also, okay? So the epsilon value is going to gradually go down, right? So this is the advantage you get. It will settle to your VRF even faster, okay? So the transient response is going to be much, much better. Okay, and then less noise mixing up with the actual signal and more noise mixing up with the actual signal. So what do you feel? Anyone? Any attempts? Less noise mix up or more noise mix up? So if you multiply this with high gain, so noise will become more or noise will become less? Anyone?
Sir, more.
Yes, more. Why is it more?
Sir, from the lectures, sir have said that if
Okay, so but you should think, right? Like why does it be okay, fine, you're right. It will become more. So let me go to a new slide. So what do you define as noise, right? So noise basically occurs at high frequencies. Okay, or let's say even at low frequencies, noise occurs. So what you are seeing is um, the system is now something like this. Okay, that is initially the system was like this, right? And now, okay, so let me erase this drawing better. So this was the system, and now you made the system something like this. Okay, pardon me, I have not drawn it as I would have liked it, but still. Okay, so something like this, right? And let's say there is a noise component over here. Okay, there is a noise component over here. So let's say this is a very high frequency noise. Okay, so let's say this is at 10 megahertz. So this is at 10 megahertz, right? And this is 0 dB, correct? So this is 0 dB, and we saw this is 40 dB, this is 70 dB, right? Arbitrary I'm taking values, and if you go below 0 dB, you will end up with minus 20, minus 40, and so on, minus 60, and so on. Okay. Now you see over here that at this node, right, at 10 megahertz, there is a noise at 10 megahertz. So let's say this is around minus 30 dB. Okay. And this is around minus, let's say how much? Minus 50 dB, let's say. So now you see that for a noise component at 10 megahertz, right? For a noise component at 10 megahertz, my original system T1, right? My original system was providing minus 50 dB gain. So if you tell minus 50 dB, that is if your dB is negative, it means attenuation, right? That is this entire range is attenuation. It attenuates the noise. That is, if X amount of noise comes, then there is going to be attenuation. That is, it may become X by 10, X by 100, or X by 1000, and so on. And over here, you will see amplification. That is the meaning of your dB, right? dB basically is amplification or attenuation. If it is positive, it is amplification. If it is negative, it is attenuation. So if I tell minus 50 dB, that is, it means that the attenuation is going to be how much you convert minus 50 back to normal domain. It will become, so what is dB? dB is basically 20 log 10 of whatever value. correct? So if you find out this value x, correct? So if you have to find out this value, then it would become how much? You need to do 10 power whatever dB divided by 20, correct? So this will give you the absolute value. So you will see that at minus 50 dB, obviously your attenuation is going to be more, correct? So attenuation at minus 50 dB is more compared to minus 30 dB. So now you understand, right? For the same noise, 10 megahertz noise, my attenuation with T2 is lesser, correct? With T2, my attenuation is only minus 30 dB. But with T1, my attenuation is minus 50 dB. So my noise rejection is better with my original system. But now that I multiply it with again, my noise attenuation is very poor. Okay. So that is why we tell that if we have gain over here, right, that is proportional gain, it can cause more noise mix up. Did you understand this? Did everyone understand whatever points we spoke of? That is, we have spoken about the steady state error, right? That is at DC. So if you multiply with gain, your effective loop gain is going to increase. Your steady state error you might know is 1 by 1 plus GH or 1 by 1 plus T as you might call it. And your closed loop transfer function will be what? T by 1 plus T. Correct? Anyway, so your steady state error is, this is your closed loop transfer function. Your steady state error is 1 by 1 plus T. So your T increases, steady state error decreases. So if you multiply with the gain, your T is going to increase, steady state error will decrease. One. Secondly, if you multiply with gain, the entire curve is going to get shifted. So your crossover frequency is going to become more. If your bandwidth of the system increases, your response time decreases. So quickly it will go and settle to the steady state value, right? So both of these are advantages. So your transient response is better and steady state error reduces, but unfortunately, you will see that the noise attenuation is very poor, correct? So in terms of noise attenuation, right? In terms of noise attenuation, if you just use a proportional gain, it is going to deteriorate your noise attenuation. Okay, fine.
Sir, what is T?
Sorry,
What is T in the slide?
what is T? T is just the loop gain.
T1.
Okay,
Okay.
and this is just a loop gain. It may be you might have studied, right? Your buck converter or any converter, the characteristic will look something like this. Okay, right? Second order system kind of a response. So yeah, this is your loop gain.
So G is also gain.
Right. So I have written over here, right? T is equal to G into H. H is your sensor gain, right? So what is your in control systems you would have right. So G is your forward gain, and then this is your Vref. This is your H. Right? So if you assume H is equal to 1, then T is almost equal to G. That's why we use the terms interchangeably. But T is equal to GH. That is the idea. Open loop gain is what? GH, right? And closed loop gain will be what? GH by 1 plus GH. Correct? So that's why I have written T by 1 plus T. Right?
Okay, sir.
Okay. Okay, so we will
Sir,
move on to the next
once
question.
could you please explain 30 kb and 50 kb? Sorry, dB.
This attenuation. Sorry, can you tell again what is your question?
You said that in 30 dB the noise attenuation is less and 50 dB it's more. That point I didn't understand.
Okay, so for better understanding, I will take another number. Okay, so instead of 30 and 50, it will complicate 30 and 50. So let me take 20 and 40. Okay. So this is fine, right? I will take, let's say this is minus 20, this is minus 40. You understand how it will be minus 20 and how it will be minus 40, right? It is just falling. So it will be a negative number. And you obviously understand that T1 will be more negative than T2, correct? So this is minus 20 and this is minus 40. Understood, right?
Yes, sir.
Okay. So now let me take another slide. So now what is dB? So what is dB? What do you define as dB? dB is
20
basically
log.
20 log 10 of whatever is the absolute value. Let me call as A. Okay. So this is the definition. So if someone tells that it is minus 20 dB for T2, right? For T2, it was minus 20 dB. So minus 20 dB is equal to 20 log A. A2, let me call it. So what will be A2? What will
10
be A2?
power A2 by 20.
10 power,
20 by.
correct?
Yes.
Correct? 10 power minus 20 by 20. So 10 power minus 20 by 20 is how much?
1 by 10.
So 0.1. Correct? Or 1 by 10? Just a second. Computer hang. Okay. And in the case of T1, you saw it was minus 40 dB, correct? So
Yes.
20 log A1. So what will be A1? 10 power
0.01.
0.01 or 1 by 100. So what it means is at this particular frequency, right, at 10 megahertz, this T2 is having a gain of 0.1 and T1 is having a gain of 0.01. So whatever frequency component I'm having at 10 megahertz, right, that will be multiplied by 0.1 in case of T2. And whatever frequency component I have at 10 megahertz, that will be multiplied by 0.01 in case of T1. Okay, so let's say X amount. Okay, let me not take X. So let's say, just a second. Okay, so let's say Y amount of noise is trying to enter the system. So your noise amplitude is Y. Okay, Y amount of noise is entering, right? This may be some millivolts or microvolts or whatever it is. So Y amount of noise is entering your system. Naturally, T1, if it has to enter T1, right? So inside T1, it will become what? It will become
Y into 0.1.
Y by 100, correct? So the noise gets attenuated. But in case of T2, it will only become Y by 10.
Tens. Yes.
Okay. So which is preferable, Y by 100 or Y by 10?
Y by
What do you
100.
want in your system? Right. So you will want more and more attenuation to noise. Okay. That is why
Yes.
you always want to have very low gain over here. Okay. This is good. But at the same time, you want very high gain at DC. Okay. So the ideal kind of characteristic for any system in general, mostly, right? So you can understand that you want to have something like this. Okay. Very high gain at DC. As you go towards lesser and lesser frequencies, you want to have very high gain. And as you go to higher and higher frequencies, you want to have very low gain. Understood, right? Why? Because this will help with your steady state error, right? And this will help with noise attenuation. And at the same time, you want to cross over at a very high frequency so that your response time is lesser. Transient response is better. Response time. Did you understand? That is high gain at low frequency. Okay, so let me write high gain at low frequency or DC, and very low gain or attenuation at high frequency, okay, or megahertz frequency, and high crossover frequency for transient response, for better response time. So high gain at low frequency will give you low steady state error, and low gain at high frequency will give you noise attenuation. Did you understand this, everyone?
Yes.
So you will study, if you would take master's level courses, the entire objective of controller design is to achieve these three. If you can achieve these three, your controller design is done and your system will be stable. And of course, yeah, you need to make sure your system is stable, right? That is, your phase margin and gain margin should be, so phase margin should be what? If your system needs to be stable, phase margin should be more than 0 degree, or phase should not go to minus 180, correct? This is something you would have studied in controls also. Anyway, so if you can design a controller that can satisfy all of this criteria, that is your controller design. Okay. Okay, so if this is fine, we will move on with the next question. In a closed loop control system, the integrator part of the controller can perform dash: high frequency noise cancellation, low frequency noise cancellation, zero steady state error, improved transient response, control of the speed of the response. Okay, so again, we will try to derive it. So they have asked about an integrator. So how would an integrator look like? Anyone? How would the integrator look like? So is it this? Will it look something like this? Will it look something like this? Or will it look something like this? Anyone? A, B, C. What is an integrator? So integrator is, if you give V in, V naught will be V in dt, correct? So what will happen to integration in the frequency domain? V naught will become V in into what? So integral will become what in frequency? Laplace transform of integrator. What will happen to Laplace transform of integrator? Anyone? I mean, there was not first.
Into 1 by S.
Correct. So into 1 by S. Oh. So V naught will become V in by S. Correct. So V naught is becoming V in by S. So you know S is equal to J omega, right? So what will happen? V naught will be V in over J omega. Correct. So if you transform this to log scale, right? So it is a 1 by omega term, right? So as omega increases, your V naught by V in will decrease. So now can you tell what is the integrator A, B or C? Anyone? I will look in the chat box also. Yeah, so is it A, B or C? Yeah, correct. So it is C. Okay, so let me take my eraser again. So your integrator response is going to be something like this, right? Agreed, right? Your integrator will be something like this. With this as your integrator, this your gain. Okay, so what can you make out from this? Okay, so this is your integrator. Okay, so now let's say that your original plant, okay, I am arbitrarily choosing, okay, your original plant was something like, let's say it was something like this, okay, it is crossing over at, let's say, 100 kilohertz, okay. Now I introduced an integrator, okay, I will introduce an integrator. So the integrator will have what? I this is your plant, and you know an integrator is having, so you can understand, right? So because V naught is equal to V in by S, so at omega equal to 0, at omega equal to 0, V naught by V in is infinity or very high gain. So at low values of frequency, right, at low values of frequency you are seeing a very high gain, right? And this gain will go on dropping, right? So your integrator will have very high gain at low frequency. So your integrator may be something like this. Okay, but unfortunately, it will fall at a slope of minus 20 dB per decade. Okay, so it will cross over very faster compared to your original plant. Compared to your original plant, it will cross over very much earlier. So now, can you tell me the new plant now? So this was your plant 1, and this is your integrator C. Okay. So what will happen to the open loop transfer function? So what will happen to the transfer function now? So just multiply, right? So this is a constant. P1 is constant. C is falling. So what will be the equivalent? Equivalent will be the system will fall, correct? Constant into a falling slope. So equivalent will be the slope will fall, correct? So the slope will fall. Slope will keep on falling. And then at this point, beyond this point, this also starts to fall. And this is also falling. So it will fall even more. Okay. So I will draw it over here. It will fall and fall even more. Agreed with this? This will be the equivalent plant. Do you guys agree with this? That is the multiplication of both of these. Just multiply the slope, okay? One slope is constant, the other is falling. So equivalent will be falling. And beyond a point, the plant also falls, the integrator is also falling. So it will fall even more. Do you agree with this?
Yes.
Okay. So now we will go back to the original question, what they have asked. So there was a plant and you multiplied with integrator, you got something like this. So what is happening? High frequency noise cancellation. Is it happening high frequency noise cancellation over here? Let's say this is your high frequency. You are having an attenuation something like this. So noise cancellation is happening or not?
Yes.
Yes, noise cancellation is happening. And what about low frequency? Low frequency, is there any noise cancellation?
No.
What happened? No, correct, right? Because originally the plant was like this, but once you multiply it with this, what will happen? Your equivalent is becoming something like this. So low frequency, there is amplification. So there is no low frequency noise attenuation. Okay, and zero steady state error. Are we getting zero steady state error? Look at the gain at low frequency. What is this point? This is a very, very high value. Very high value, right? So ESS is equal to 1 by 1 plus T. T is very high. So ESS will be very low. So you are getting zero steady state error. Agreed? Is this fine? You are getting zero steady state error.
Fine, sir.
Okay. And what about D? Improved transient response are we getting? So see, originally the system was crossing over here. Okay, you added an integrator, the integrator crossed over here itself. Okay, the integrator crossed over here itself. Originally the system was crossing over here. So what happened to the transient response? Will it become faster or slower system?
Slower,
So,
I guess.
correct, right? Because see, your integrator is passing off even faster. It is passing off the 0 dB even faster, right? Okay, so as you can understand, the system is going to pass cross at a very low frequency, right? The system will cross off at a very low frequency. So let's say this was omega 1, this was omega 2. This omega will be less than omega 2 definitely. Okay, this the equivalent transfer function, the equivalent system will pass off even faster. Okay, so what is happening? Your integrator has made the system, sorry, so omega will be even lesser. Okay, omega will be even lesser. So if your omega is less, then omega is less, so system will be slow or fast? System is what?
Slow.
Yeah, so system is slow, so the system has become slow now. Okay, so will we get improved transient response? No, right? System is
No.
slow, we will not get improved transient response. Okay, and control over the speed of the response. Are we getting control over the speed of the response? Can we get control? So let's say the integrator is like this, right? This is minus 20 dB per decade. The integrator may also be like this. The integrator may be like this. The integrator may be like this, right? So I can vary what is this point. I can vary the gain of the integrator. Okay, if I can vary the gain of the integrator, then based on whether this is this or this or this or this, the omega will change. Correct? Based on this, the omega will change. This omega will change. If my omega changes, the system transient response will change. Agree? Right?
Right, sir.
Right. Okay. So this is not very clear over here that whether there is a gain, whether it is simply 1 by s or whether it is a by s. But the idea is if you have an a by s, you can vary a. If you vary a, your response will change. But if it is only 1 by s, you don't have any control. Okay. 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 So we'll move on to the next question. So which of the following is a possible Bode plot for PI controller? Kp plus Ki by S. Okay. So let me take a new slide over here. So what is given? Kp plus Ki over S, correct? This is what is given. So always you try to analyze in terms of, so this is equal to j omega, correct? Always try to analyze at omega equal to 0, at omega equal to the resonant frequency omega r, and omega at very high frequency. Okay. Okay. So Kp plus Ka by S is what is given. Okay. So at omega equal to 0, let's say, so Kp plus Ki by J into 0. So what is the value? J, so 1 by 0 is infinity. So at very high gain at low frequency, correct? So what does it signify? Very high gain at low frequency, right? Agree? Okay.
Yes.
Then let's say at omega equal to infinity, that is very high frequencies I'm going. So Kp plus Ki by J into infinity, correct? So 1 by infinity is 0. So Kp plus 0 will be simply Kp, correct? So as you go towards higher frequencies, you should see a fixed Kp, correct? A fixed value of Kp you will see. Okay. So now you tell me from this, what satisfies our requirement? A or B or C or D or E. That is at low frequency, high gain. Okay. At high frequency, value is simply Kp. So what is the answer? Anyone? Okay. So another hint I will give you. You try to split it. So what is this basically? Kp plus Ki by S. Correct. So if you multiply any plant transfer function, you can write plant into Kp plus plant into Ki by S. So just see, this is just a proportional controller and this is just an integrator. So integrator will have something like this and a proportional controller will have something like this, constant. Correct? You just mix both of this, you will get the answer. Okay.
Option B.
Option B, right? So this can be one solution. Correct. Correct. So at low frequency you have a high gain, and at high frequency you have a fixed gain. Okay. Option B. Any other thing that satisfies our requirement?
E also, I guess.
Correct. Did you guys understand others? B, why B and D, as she is telling? Why B and D? Because you see over here at low frequencies, what is your gain? And at high frequency, what is your gain? Okay. Just see it asymptotically, you will get the answer, right? Obviously, you cannot have A because this is kind of like a differentiator. This is S term. So this is something like so this is something like Kp plus S into KD if you have a differentiator. So S term is there. So as frequency increases, your gain also increases, correct? As you go to higher and higher frequencies, your gain is increasing. So there should be a J omega term. So Kp plus S into Kd as S is equal to J omega. So omega increases, gain increases. Agreed, right? And this is simply 1 by S term. We have already seen this, or Ki by S term. Okay. So yeah, only two are satisfying, that is B and D, right? This is your Kp plus Ki by S. Okay, so we move on to the next question. Slope compensation is not required for this inductor current. True or false? Anyone? Quickly. Slope compensation is required or not? Just see the inductor current. Whether the inductor current is in CCM or DCM.
So DCM.
So yes, it is in DCM. So if it is in DCM, slope compensation is required or not?
It is matching.
Sorry, it is?
It will not required.
Correct. Slope compensation is not required. Okay. So true, slope compensation is not required. Okay. So calculate the value of slope compensation capacitor used in the current control circuit when the inductor current waveform has a slope of 0.5 ampere per microsecond. So di by dt for the inductor current, correct? This is 0.5 amps per microsecond. Okay. So what is the value of C during T off? Right, the constant current used to charge up the compensation capacitor is equal to 1 ampere. So I is equal to 1 ampere. Okay, and your slope is also given, right? So and note, slope compensated is considered equal to inductor current waveform slope during T off. So during T off, the di by dt is given as 0.5 ampere per microsecond. Slope unit is volt per microsecond. Okay. In terms of, in case of capacitor, and ampere per microsecond in terms of inductor current. Okay, so again, this is directly you can get the answer from I is equal to C dV dt. So I is given as 1 ampere. Okay, so dV dt is 0.5 volt per microsecond. Okay, correct. That is I constant by Cs is 0.5 volt per microsecond. So your C will be simply 1 by 0.5, that is 2 microfarad. Right? Simply from I equal to C dV dt, we obtained it 1 by 0.5 answer. Okay, fine. Okay, so we are going to the inverter part now. So I'll just have a break of 2 minutes. I will drink some water, and yeah, from here we will continue. Okay, just we will break for 2-3 minutes and we will continue. Okay, so let me start now once again. So a carrier wave of frequency 1 kilohertz is compared with a reference wave of plus or minus 2 plus 2 volts as shown below. Calculate the duty cycle of the output waveform for the following logic. Okay, and note output equal to 1 if your reference wave more than carrier wave means T on period, else 0. Okay, so you can understand that this is your duty, right? And this is your carrier VC. And if you know that if your Vref, correct? If your Vref is more than Vc, then D equal to 1, else D equal to 0. So here itself you can understand from between this to this, correct? That is your Vref is more than your Vc, then your duty will be on. So between this point to this point, your duty will be on. And then between this point to this point, correct? Your duty will be on. And the cycle continues. Understood, right? So you can calculate based on this. Okay. That is the peak is given as 5 volt. This is 2 volt. So you can compute what should be the value for this. Okay. Okay. So you try to understand this, that let me take a new slide again. Okay, so in that case, you can understand that for this period, correct? That is during this period, that switch is going to be off, and during the rest of the period, the switch will be on. That is the definition, right? During this period, that is your carrier is more than your reference, your switch will be off, and during the rest of the period, the switch is going to be on. Okay. Just compute by similar triangles. Okay. That is you just need to find out this value, right, and subtract it from TS. Then you will get the switch on period. Okay. Okay. So what will be this value, right? So the peak is 5 and reference is 2 volt. And you know that this total period is TS by 2 and this is TS by 4. Okay. This point is TS by 4. Okay. So you can tell, you can understand by virtue of similar triangles, right? That is 2 by 5 is equal to what? Is equal to this period by this period. So let me call this as x1. So x1 divided by total period, that is TS by 4. Let me erase this. So this is TS by 4, right? This is TS by 2. Okay, so x1 will be what? 2 by 5 into Ts by 4, correct? So this is going to be simply Ts by 10. So did you understand how we got x1? This is by similar triangles. Okay, that is, we just divide, right? That is, let's say there are two triangles. This is one triangle and the other triangle is, so this is one triangle and the other triangle is something like this. Okay, so in that case we tell, let me call this as A, B, C, D, E. Then we tell that what BC divided by DE is equal to AC by AE. Understood, right? This is what is called a similar triangle. So by that way we have found out what is x1, right? And similarly, if this is x1, this is also x1, correct? And of course, you know that for the rest of the period, the device will be on. This is Ts by 2. So the total on period will be what? On period is equal to what? 2x1 plus Ts by 2, right? So, yeah. So, 2 into Ts by 10 plus Ts by 2, correct? So, Ts by 5 plus Ts by 2. So, it will be Ts by 5 plus Ts by 2 will be what? 5, 5 Ts by 10, correct? So this will be what? So 2 Ts by 10 plus, so this will be 7 Ts by 10, or duty, or your D is equal to 0.7. Did you understand this, everyone? We have just found out what is this area.
Explain one more time.
Okay. So let me take a new slide. See, they have given something like this. Let me draw it big. Okay. And they have told this is the reference, and this is not according to scale. Okay. So we can mark it later, but okay. So let's say this is
So
5.
are we finding only for one cycle?
Yes, because they have asked the duty, right? Calculate the duty cycle. That is in one cycle, right?
Okay. Okay.
So this is 5 volt and this is 2 volt. Okay. So let's say this is your 0 point. Okay. So this is 0. This is, so this is Ts by 2 and this is Ts. Okay. So this is one cycle, from 0 to Ts is one cycle. And they have told that if your blue is more than red, then the switch is on. Okay. Your blue is more than red, then the switch is on. And let me mark the other markings as well. So this is Ts by 4. Okay. So when is your blue more than red? Your blue is more than red during this interval. That is between this to this. Then it is 0. And between this to this, the switch will be on. Agreed?
Yes, sir.
Okay. So you just need to find, so if you take within one cycle, right? If you take within one cycle, that is between 0 to Ts, you should find out the area of this That is not the area, that is the time period for which this violet thing is on. That is within one cycle means till this point. Agreed?
Yes, sir.
Okay. So now the point is, we have to find out what is this. Okay, I am calling it x1. If this is x1, this will also be x1. Agreed? Between this point to this point. This is just symmetric, correct?
Sir.
This 2 volt will cut this triangle over here. The same 2 volt will cut this triangle over here. So the slope is same for the triangle. Okay. So this will be same x1. Agreed?
Yes, sir.
Okay. So between Ts by 2 to Ts, you know that the distance is simply Ts by 2. So this is Ts by 2. Correct? Agreed? So the total on period will be what? X1 plus x1 plus Ts by 2. Correct? 2x1 plus Ts by 2. Correct or not? Agreed?
Yes, sir.
Okay. So we just need to find out what is x1. Then our answer is done. Right? So for that, we are applying the similar triangles method. That is, let me zoom in over here. Okay. You consider this particular region. So what is happening? So let me draw this for ease. So your triangle is increasing something like this. Okay. 0 to, this is the problem, 0 to 5. And you have your blue waveform somewhere over here. Okay. This is your 2 volts. So what you get is eventually, yeah. So what you get is eventually something like this. That is, the switch is turning off over here, right? So you need to find out, and you know that this is your x1. Okay, this is your x1. So now I will complete this triangle. Okay, that is, this is one triangle, and this is another triangle. Okay, and you know that this entire period is what? Entire period is Ts by 4. We have marked it 0 to Ts by 4. This is Ts by 4. Okay. So now you can understand that, let me call this point A, B, C, D, E. By similar triangles property. By similar triangles property, you know that BC, right? This BC divided by DE, shorter side by longer one, is equal to the perpendicular ones. That is AC divided by AE. Did you understand this?
Yes, sir.
Okay. So what is BC? BC is 2 volts, correct? 2 volts is the point. 2. What is DE? DE is 5 volt. Is equal to what is AC? AC is X1. And what is AE? AE is TS by 4. Therefore, X1 is what? X1 is 2 by 5 into TS by 4. Agreed? TS by 10.
Yes, sir.
So now you substitute this back over here, 2x1 plus ts by 2. So 2 ts by 10 or ts by 5 plus ts by 2. How much will you get? 2 into ts, 5 into ts. So 2 ts plus 5 ts. So 7 ts by 10. Or duty cycle is 0.7 or 70%. Did you understand? How we got this?
Yes, sir.
Okay, simple, right? Just apply triangles property, you will get the answer. Okay. Okay, so let me move on. Yeah. So for the converter given in the figure, Q1 and Q4 are kept on for 20 milliseconds and Q2 and Q3 are kept on for 20 milliseconds. The resultant voltage waveform across A and B is dash. Okay. So can anyone tell the answer? When Q1 and Q4 are on, what is VAB? So Q1, Q4 are on. Okay. So what is VAB? So there is VCC over here. Okay. And Q1 is turning on. So VCC appears over here. And Q4 is turning on. So Q4 is turning on. So ground appears over here. So what is VAB during this point when Q1 and Q4 are on? Okay, so tell me something. So correct, VCC. And when Q2 and Q3 are on, Q2, Q3 are on. What will be VAB? When Q2 and Q3 are on? See, when Q2 is on, right? So the ground will appear at point A and Q3 is on. So VCC will appear at point B. So what will be VAB? VA minus VB, right? So VA is ground, VB is VCC. So 0 minus VCC, that is minus VCC. Agreed?
Yes.
Okay, just a second. So now you understand that for 20 milliseconds, right? For 20 millisecond, Q1, Q4 are on. So for 20 millisecond, you will see VCC. Okay, for 20 millisecond, you will see VCC. And for the next 20 millisecond, Q2, Q3 are on. So you will see minus VCC across VAB, minus VCC. And this cycle will repeat. So you will get something like this. Agreed? So the answer is what? C. Does everyone get this?
Yes.
Okay. Thank you. Okay. So referring to question number 9, the switching frequency of the transistor Q2 is dash. So what is the switching frequency? So what is switching frequency? So switching frequency is the frequency at which the period repeats, right? That is the pattern repeats. So you see 20 millisecond on and 20 millisecond off, and it is kind of repeating. Correct? So what is the frequency? So the total period is how much? 40 millisecond. This is the period, right, which is repeating. This is the waveform which is periodic. So your total time is 40 millisecond. So T is equal to what? T on plus T off. So 20 millisecond on plus 20 millisecond off. So it gives you 40 millisecond. Therefore, frequency will be 1 by T or 1 by 40 millisecond. Okay. So what is 1 by 40 millisecond? Hertz. Okay. Sorry, not 250 hertz, 25. Right. 25 hertz, correct?
Yes.
Yes. Okay, so I hope till this point it is clear. We'll move on to the next question. So the figure below shows that a single phase inverter is used with a resistive load. So there is a single phase inverter and there is a resistive load. So the load is resistive. Okay. The modulation scheme is also shown in the figure. Specifications are as follows. VDC is 300 volt. C1 and C2 are 2200 microfarad, initially assumed to be charged. ZL is 100 ohm. TS is 0.02 second. All switches are ideal. If the sine wave is amplitude is 0.85, right? So sine wave is amplitude is 0.85. So the peak value is 0.85. Okay. Then find the peak amplitude voltage between points A and B. Between points A and B. Okay. So this is what kind of PWM? Anyone? This is what kind of PWM? What is the reference and what is the carrier?
Reference to sine wave.
Reference is
Triangular
sine
is
wave.
the
Carrier is
carrier.
triangular. Okay. So what is the PWM called? Is it uniform PWM or constant PWM, or what do you call it? What is this kind of PWM? So we call this as sinusoidal PWM, right? So if you compare it, you will get pulses something like this.
Quasi square wave.
Right. And so on. Okay, so you'll get something like this. So the output voltage, it turns out, you might have learned also that V naught is M times VDC, correct? So the peak amplitude voltage will be what? This is the peak, right? So 0.85 is your M, that is the sine wave's amplitude, into VDC. VDC is 300. So 0.85 into 300, correct? So that will be your voltage. Okay, that is around 255 volt. Okay. Right. Okay, so I will, in the interest of time, I will move on to the next question. This is again on the sinusoidal PWM. You just need to find out what will be the value of at 0 TS by 2 and TS. So I think the solution is also given. You can figure it out yourself, but I will move on to the next question for now. Okay, so what is the maximum voltage that appears across any device? So even though your average voltage is 0.85 into 300, right? Your average voltage is MVDC. The maximum voltage will still be VDC when the device has to block voltage, right? The maximum voltage will still be VDC. If S2 is on, entire VDC is going to come across S1, and if S1 is off, then entire if S1 is on, the entire VDC has to be blocked by S2. So this voltage rating of switches, right? The voltage rating of switches, voltage rating of switches is equal to VDC. It will not be MVDC. MVDC is the average voltage across this load. Okay, average voltage across this load will be MVDC, but the switches still need to block the entire VDC. So VDC is 300 volt, so the switches need to block the entire VDC. Okay. Okay. So in the figure below, the asymptotic plot of a PI controller is plotted. What is the value of omega 2 in radians per second? Okay. So omega 1 is given as 0.1. Okay, this is 0.1 radians per second. What is omega 2? Again, just try to understand. at omega 1 equal to 0.1, right? Your gain is 30 dB, right? At omega 2, the gain is minus 20 dB. Okay, and it is given that it is a PI controller. So if it is a PI controller, we just saw it in one of the previous problems. The plot will be, I think one of you also answered it, right? That is, the plot will be either B or E. It will be something like this. Okay. So what is the slope of this fall? Can anyone tell what will be the slope? What will be the slope of this fall for a PI controller?
So y2 minus y1 upon x2 minus x1.
Correct. So that is x1, y1 are given and x2, y2 are given. That is the slope. But in this question, see, you don't know what is y2. Correct? You don't know, sorry, you don't know what is x2. Right? Here you don't know what is omega 2. Slope is, as you told, y2 minus y1 by x2 minus x1. But you don't know what is omega 2. So what is the slope of this? What is the slope is my question. The hint is they have given it's a PI controller. Okay, that's an integrator. Correct? So integrator and a proportional. So what is the slope? Anyone? What is the slope? So see, you take an integrator, okay? PI is nothing but proportional and an integrator only. So integrator will fall something like this. So we have to find out the slope. Okay. So you know, integrator is simply gain into 1 by s, or let's say 1 by s for now. Okay. So 1 by s or 1 by j omega. So the magnitude is simply what? 1 by omega, right? That is your magnitude. So you take the dB of this. dB is equal to 20 log A. So at, let's say, omega equal to 10 hertz. Okay. dB will be 20 log 10. What is 20 log 10?
20s.
20.
20. At omega equal to 100, right? What is the dB?
40s.
Correct. 20 log 100. Log 100 is 2. So you get 20 into 2, that is 40 dB. Sorry, it's 40. So what has happened? As you went from 10 to 100, that is, there is a decayed increase in frequency. That is, decayed increase in frequency. Correct? That's a decayed increase in frequency from 10 to 100. Then your dB decreased from, or your dB kind of went from 20 to 40. Correct? So, okay. So, yeah, okay. So there is one small error that we did. That is 20 log A or 20 log 1 by omega. So 20 log 10 nahi, 20 log 1 by 10, right? Or 10 inverse. So if there is 10 inverse, minus 1 will
Minus
come
20.
outside. It will become minus 20 and minus 40. Correct? Agreed?
Yes.
So what happened? For a decayed increase in frequency, my dB decreased by minus 20. Agreed? So
Yes.
dB has decreased by minus 20 dB. So this slope can be told as minus 20 dB per decade. That is for 1 decade increase in frequency, my slope is or my gain has decreased by minus 20 dBs. Okay. So if I go from 1 kilohertz to 100 kilohertz or 1 kilohertz to 10 kilohertz, my dB will decrease by minus 20. Okay. Did you understand? What did we tell? That is the
Yes.
slope is minus 20 dB per decade. So for example, let's say, I'll just give you an exercise so that you guys get familiar. At 1 kilohertz or let's say at 10 kilohertz, my gain is 70 dB arbitrarily. So at 100 kilohertz, what will be my gain? And at 10 kilohertz, and let's say at 100 hertz, what will be my gain? Can anyone tell? At 10 kilohertz, my gain is 70 dB. Okay. At 100 kilohertz, what will be my gain? Okay. So first, gain will increase or decrease? Anyone?
Decrease.
Sorry?
It would decrease.
It will decrease because there is a falling slope over here. As frequency increases, gain decreases. Correct. So 10 to 100, is it a decade jump or what? It is a decade jump, right? That is 10
Yes.
kilohertz to 100 kilohertz. That is a decade. So then what will happen? The slope is minus 20 dB per decade. So what will be the gain at 100 kilohertz? Sorry. So yeah, what will be the gain at 100 kilohertz then? At 10 kilohertz, it is 70 dB.
140.
No, see, understand. It is minus 20 dB per decade. So for 1 decade, there is a decrement of minus 20. At 10 kilohertz, it is 70 dB. At 100 kilohertz, it will become 70 minus 20, 50 dB. Understood? That is 10 to 100, 10K to 100K is 1 decade. Okay. So for
Yes.
1 decade jump, the gain will decrease by 20. Correct? Did you understand this?
Yes.
Okay. And similarly, if let's say I go from 100K to 1 megahertz, then what will happen? Again, 100K to 1 megahertz is 1 decade
Minus
jump.
20, 30 dBs.
Correct. So 50 minus 20, that is 30 dBs. It will become 30 dB. Okay. Let's say you go from 1 mega to 10 mega. It will become 30 minus 20, 10 dB. Correct? Okay. 10 megahertz to 100 megahertz. It will become 10 minus 20, that is minus 10 dB. You understand, right? How it progresses. Okay. Okay. So now you tell me at 10 kilohertz, we are having 70 dB. Okay. At 100 hertz, what will happen? So go back. 10 kilohertz is 70 dB. So 1 kilohertz, at 1 kilohertz, what will we have? What will we have? Anyone? Again, a decade jump we are doing. What will happen at 1 kilohertz? We are going towards this side.
Increase.
So it will
Increase by 40 dB.
so 100 hertz will be 70 plus 40 dB. That is 110 dB. You agree, right?
Yes.
Is this fine? So now that you have understood, let me draw this. So we previously saw that. So let's say integrator, some integrator. I call this as A by S. So it will have something like this. Okay. So arbitrarily, let me mark this is at 1 kilohertz. Let me take some other example, okay? And this is, let's say, 37 dB. 37 dB at 1 kilohertz. I want you guys to fill up for 100 hertz, 10 hertz, 10 kilohertz, 100 kilohertz. Did you understand the problem? Okay. So what will be at 100 hertz? Can you tell?
57.
Correct. I think with the Bode plot, it is easier to visualize, right? Now you can, I think, easily understand. Correct?
Yes.
Okay.
77.
At 10 hertz, what will happen? Yeah, at
77.
10 hertz. 97. Simple, right? Now it seems very simple. This is minus 20 dB per decade. So 1 decade means in log scale. So what is 1 decade? 1 decade can be 1 hertz in powers of 10. In powers of 10. Okay. 10 power 1, 10 power 2, 10 power 3. So this is 1 decade. 1 decade. 10 power 2 to 10 power 3 is 1 decade and so on. Okay. Okay. So what will be at 10 kilohertz?
17. 17.
Correct. 17 dB. And at 100 kilohertz?
-3.
Correct. -3. Okay, I have not drawn it properly. This is not exactly zero line, but you get the idea, right? That is, if we tell that something is decreasing at -20 dB per decade, you understand, right? What is -20 dB per decade? Everyone, is it fine? Akshit Kapoor.
Yes, sir.
Okay, is it fine, right? It is fine, right? Okay. So now we will come back to the original thing. So this was obtained for an integrator. Okay, for an integrator, that is any term that has 1 by j omega. You will see that, let's say I tell not 1 by s but 1 by omega, 1 by s square. Let's say there is something that is 1 by s square. You understand that it will be minus 40 dB per decade. Makes sense, right? In dB scale, power square will become into 2. Correct? Did you understand? This is just an extra thing that's not required, but still I'm trying to make you guys understand. If I tell 1 by s cube, it will become minus 60 dB per decade. Okay.
Yes.
Okay. So now this was 1 by s. Let's say the term is only s. A into s. What will happen if it is only A into s?
Plus 20 dB per decade.
Correct. Simple. So that is what is the differentiator, right? Differentiator is what? Differentiator is into s. D by dt becomes s, right, in frequency domain. That is d by dt in frequency domain becomes s. So what will happen? You will get something like this. Arbitrarily I'm drawing. So now what will happen? This is plus 20 dB per decade. As frequency increases by 1 decade, your gain will increase by 20 dBs. Okay. So let's say arbitrarily I take, this is some, let's say this was 24 dB. Okay. 24 dB. At, let's say this is 100 or 10 kilohertz. Okay. So let's say instead of 10 kilohertz, let's say I take this as 20 kilohertz. Then at 200 kilohertz, what will be the gain? Are you understanding? At 200 kilohertz, what will be the gain?
44.
44 dB. 20K to 200K is also 1 decade. Okay. Similarly, this is 24 dB at 20K. At 2K, what will be the gain? At 2 kilohertz, what will? Huh? Yeah. So this will be 4 dB. Correct. So now you get the hang of it, right? So this is a differentiator. Differentiator. This is integrator. Okay. Fine. Now we will go back to that problem. They told it was a PI controller, correct? So what is the slope? If this is PI, this is minus 20 dB per decade. Okay, fine. So with this known as Akshit told, slope is y2 minus y1 by x2 minus x1, correct? So minus 20 is the slope is equal to y2 minus y1. So what is y2? So let me call this as x1 y1 here, and this is x2 y2. Okay. So yeah, minus 20 is equal to what? So y2 is minus 20, correct? Minus 20, and y1 is 30 dB. So divided by x2 minus x1. So remember that this is in log scale. Okay, this should be in log scale. This is log. So log omega 2 minus log omega 1. Okay. If you solve this, you will get what is omega 2. Minus 20 is equal to minus 50 divided by log omega 2 minus log omega 1. So what is log of 0.1? Log 10 is 1. So log 0.1 is
minus 1.
Okay, so minus 1. So minus of minus 1 is plus 1. Okay. So you just solve it, you will get what is omega 2. Did you understand this? This is a very important problem. Never forget this log. Okay, that is one thing is this is minus 20 dB per decade. Even after knowing minus 20 dB per decade, many people do not include this log over here. You should remember that the frequency scale is on one side, this is linear and this is log omega. Now, if you want to calculate the slope, you should take that log thing into account. That is log omega. Okay, not just omega 2 minus omega 1. It is log omega 2 minus log omega 1. Will you guys remember this? Log omega 2 minus log omega 1. You should remember. Okay, don't ever forget. Don't write omega 2 minus omega. It should be log omega 2 minus log omega 1. Okay.
Excuse me, sir.
Yeah.
Sir, do you know how to calculate inverse logarithm in scientific calculator, TCS-IO?
In scientific calculator, that is this 10 power option, right? So what is inverse log? 10 power, whatever is your dB divided by 20. So there is an option of 10 power. You look in your calculator, there will be 10 power. One option will be there.
Okay.
Or you just type in YouTube, it will give you, but I know I have 10 power option is there. So I think the font will be written something like this. If I remember right, 10 power or 10 something like this was written in my calculator. But yeah, this is the symbol. Okay. Because it's log 10, like log to the base 10. Did you understand this? This is the solution anyway. So you will get around 31.62 radians per second. Okay. Okay, so I think you have seen enough problems. There are even more problems we can Anyway, I will upload all of these in the drive. You can have a look at it. Okay. I don't know why my screen is not closing. Okay, so you can have a look at it. And do you guys have any doubts so far? And thanks everyone for hanging around. I know it's around 15 minutes part time. Yeah, it's 31.6. Correct. It's 31.62 readings per second. I know it is part time, but thanks to everyone for hanging around. If you are fine with it, I can discuss the remaining problems quickly, or if you want me to wrap up, I can wrap it up now itself. Any suggestions? Do you want me to go through the remaining problems quickly, or is it fine? Can I just upload it? Okay, so okay, fine. I will go through it then. Just give me around 5-10 minutes. We can review quickly. Yeah, we can see that quickly. Okay, so in the DC-DC converter shown below, Q1 and Q4 are identical gate drives of duty cycle Ds, which Q2 and Q3 bases are shorted to the respective emitters. Find the input-output voltage relationship. Okay, so this is a DC-DC converter. So for any DC-DC converter, how do you find out the input-output relation? Across L, you see the voltage. So that is what is VL during DTS period and what is VL during 1 minus DTS period, right? And then apply volt second balance. Correct? So this is what you follow every time. So let's do the same thing. Okay. So since they have given that Q2 and Q3 bases are shorter to the emitter, so base is shorter to emitter, right? Base is shorter to emitter. There is no AB current flowing, so Q2 and Q3 are always off. Okay, Q2 and Q3 are always off, and you obviously have the anti-parallel devices. Okay. Okay. So now you tell me something. Please participate. Okay, this question is an interesting question. You might get some other converter but with a similar problem. Okay, this is a very commonly asked question, right? So let's say Q1 and Q4 are on. Okay, that is DTS period. So Q1 Q4 are on. Okay, so what is VL during that period? VL will be in the plus region. You have V in, and minus is connected to what point? Q1 is on. So Q1 is on, so it will be connected to plus minus V out, correct? So V in minus of minus V out. That is V in plus V out. Did you understand this? That is Q1 is on. Okay. So the connection is something like this. Let me. Okay. So it is V in minus of minus V out. So V in plus V out. Right. And when Q1 and Q4 are off. Okay. So when Q1 and Q4 are off, Q1, Q4 are off. So what will happen to VL? Q1 and Q4 are off. Therefore, it will be connected through the anti-parallel diode to V out. Correct? So it will be V in the plus side
Minus V out.
This will be minus V out. Q2 and Q3 are on, right? So through the anti-parallel diode, it is directly connected to plus V out. So V in minus V out, right? Because this is correct. So V in minus V out. This is during the 1 minus period. Okay. So yeah, okay. So I think you want that V in minus V out. Correct. Yeah. Okay. So what is your VL? VL is equal to V.
Sir, your voice is echoing.
Oh, I mean, audible. Should I repeat the counter normally? No, it's fine.
No, sir, it's actually echoing.
Oh. Okay, so I speak slowly only, and we are also very much of time. But anyway, this understand that you should find out what is VL during the non. That is also when Q1 Q4 are on, find out VL, Q1 Q4 are off. So you will get, you obviously know that average value of VL over a life cycle is 0. That is over a switching change is 0. So V in plus V naught into DDS plus V in minus V naught into 1 minus D is equal to 0. So you solve this dV plus dV naught plus V minus V naught minus dV plus dV naught equal to 0. So dV minus dV get cancelled. So you get dN is equal to V naught minus 2 dV naught. So V naught by N is equal to 1 by Y minus 2 dV. Did you understand how this is coming? If you have understood, I can proceed. Right. This is fine. You just calculate what is the inductor voltage. So V plus is always V in. Okay. V minus over here. When Q1 Q4 are on, when Q1 is on, it is connected to minus V out. And when Q1 Q4 are on, and when Q2 Q3 are on, it is connected to plus V out. So VL is equal to VN minus V naught. VN plus V naught during VN minus V naught during is this fine? You can just give us some if this is fine or you want me to explain something in the creativity. Okay, so I think there is a issue which made my voice. Okay, so there is some issue, I guess. If this is fine, we can really go here. So if you're not looking my voice, then it's not good to continue. So I think I can conclude over here. There are just a couple of problems remaining, and I think you can go through that by yourself. Okay. All the update solutions are given in the questions and all my questions, and it's okay. You can just go through it. Okay. So yeah. Thanks everyone for hanging around. I know it's been a very long time, but thanks everyone for hanging around and being very interactive in this class. I found this class very last class and yeah, most of all of you have attended well, very sincerely. So I really appreciate your attendance and yeah, if you have any questions, go ahead. You can reach me and get Miss Lady if you want. in case you have any doubts. But anyway, good night and have a great day. And all the best for your course and whatever you are going through, right? Whatever it is, master, bachelor's, even PhD. So, yeah, thank you very much for attending and all the best. So, and let's stop sharing and we can end for the day. Okay. Yeah, thank you very much. Yeah, thanks for the attending.